Hi, and welcome to the next lecture of 6838. Now, in the last couple lectures of this course, we discussed a really classic problem, especially in differential geometry, which is, given a description of a geometric domain, how can we extract shortest path distances between points? Today, we're going to start asking a sort of reverse question to that. Namely, let's say that I'm given a bunch of points, but I forgot where they were. But what I do know is the pairwise distances between those points. The question is going to be, can I recover the geometry from that information? Now, this problem might sound pretty abstract, like when would we be given distances but not geometry? But it turns out to be extremely practical. So for example, when we want to visualize a data set, oftentimes we know things like similarities between data points, or we have an embedding of our data, but it's into an extremely high-dimensional space, and our task is to embed it into some lower dimensional space that we can visualize while still preserving the structure that we care about. So these are the sorts of problems we're going to consider. Unfortunately, our discussion doesn't fit totally neatly into 2 lectures, but that's the amount of time I've reserved for this discussion. So I'm going to divide our discussion among a few shorter segments, and in class time we may have to divide up our videos so that they fit the MIT hour-and-a-half long lecture schedule. But in any event, that's not a big deal. So as a little bit of review, essentially in our previous couple lectures, you can understand what we've done as this little schematic here, right? So our input data is a description of a piece of geometry. We focused on triangle meshes, or really just more general mesh-like objects where you can do things like the fast marching algorithm. And maybe given one of these mesh domains and given one point or a few source points, we talked about how to compute distances between these different points using these different algorithms. So in other words, our input was an embedding, and our output was something like geodesic distance. Today, we're going to ask a different question, which is, given distances between points, can we flip this arrow backward and actually recover an embedding? And there's so many different versions of this problem. So for instance, just like I've written on the slide here, one of them would be given geodesic distances between points on the bunny. Can you reconstruct the bunny? The answer is generally no, but that's something we'll defer on a little bit. An even simpler one would be given just extrinsic Euclidean distances between all the pairs of points on the bunny. Can I reconstruct that bunny, at least up to maybe rigid motion, translation, rotation, and so on? Then things become a little bit murkier, but also more positive, that there's actually some things that we can do. Now, this basic task comes with many different names, and most likely you've seen one if you've taken, for example, a machine learning or statistics course, right? There are many different overlapping tasks that all have to do with taking some metric, similarity, distance structure, and embedding it into a geometric space. Typically Euclidean space, but not always. So for instance, some of the different terms that you might hear are dimensionality reduction, embedding, parametrization in computer graphics, manifold learning in graph theory and in machine learning, and so on. All of these different tasks have a very similar flavor and actually can be described using roughly similar language, which is kind of useful in our 6838 course. So the basic test that we're going to consider looks something like this. Given a list of pairwise distances between points, so in the discrete case, I could think of that as just a big matrix of numbers given distances between points on some domain, where I forgot the locations of the points in 3D or in some other dimension. Can we extract an embedding? So can we actually place those points in our space so that the distances between these points resembles the input data, either exactly or approximately? Now, in this first short lecture segment, before we talk about algorithms for this task, we're first going to ask a few theoretical questions. Things like, is it always possible to extract an embedding? Maybe which space are we embedding into? Like, is it Euclidean space? Is it L-infinity? Some other one? Now, even if I want to embed into Euclidean space, the answers are still a little tricky to these questions. For example, can I embed my data into 3D might be different from can I embed my data into n-dimensional space for some n, which might be different than can I embed my data into LP for some other p, and so on. So there's so many different versions of this basic question. It could easily fill an entire textbook worth of discussion, but of course, instead of that, we're going to dedicate maybe 30-40 minutes to it today. So before we examine these questions more closely, of course, it's important to know what we're up against, in particular to make our definitions a little bit more clear. So the basic object that we're going to work with in this series of lectures is actually much weaker than the manifold structure that we've focused on so far in this course. In particular, rather than thinking about manifolds which have smooth structure, they're locally Euclidean, and so on, in today's lectures, we're going to think about just dealing with metric spaces. Now, very generically speaking, a metric space is just some space equipped with a distance function d, right? So a manifold is an example of that, right? And over the last two lectures, we defined what it means to be a distance function on a manifold by really working out carefully the geodesic distance function in many different contexts. But there are many other spaces that are metric spaces but not manifolds. So for example, we'll see that graphs with the shortest path distance would be an example, or just a collection of points in n-dimensional space equipped with the pairwise distance between those points. Now, generically, when I talk about a distance metric is a function d of x comma y that satisfies these four properties that I've given on the screen. And roughly these four properties are intended to abstract away what it means to be a distance function. Now, I think basically these four properties are really intuitive, and it's somehow the mathematician's minimalistic set of what we really need to do geometry in some very vague sense. So, for example, I think we can all agree that distances are positive, right? That's our first example. Typically, by the way, it's not just that distances are non-negative. This is technically not a metric space unless you add the second condition, which is that distances are zero exactly when 2 points are equal to one another. Right? So in other words, the only time that 2 points are distance zero to one another is when they're the same. The third property is telling us that the distance function is symmetric, right? So the distance from x to y is the same as the distance from y to x. And then finally, we have the most famous property of all. And this is the one that I would argue is basically the only thing we use to prove a lot of theorems. And this property is called the triangle inequality. Now, the triangle inequality is something you've probably all seen before, but it's just an axiom about a distance function or a metric space that says that the fastest way to get from x to z is always to go directly. So in other words, the distance from x to z is always upper bounded by the distance from x to y plus the distance from y to z for any other y. There's never a case where going through y somehow decreases the distance rather than going directly from x to z. That's what this third property, the triangle inequality, is trying to tell us. Now, there are so many different examples of metric spaces, and I think most of the students in this course could rattle off many of them. If we were live in a classroom, I would take a survey. But here are a few examples. So one is Euclidean space, Rn, equipped with the p distance. Remember that the p distance I should have put p for p greater than or equal to 1. Is just the pth root of the sum of the absolute values of the pth powers. Now, in the last couple lectures, we developed geodesic distances along surfaces, and actually we didn't check it explicitly, but you can check easily enough that geodesic distances satisfy the triangle inequality. If I remember, that would probably be a good homework problem. And in fact, metric spaces can even be really, really large and much bigger than just basic finite dimensional Euclidean space. So for example, the set of infinitely differentiable functions over the real numbers equipped with this sort of integral metric is yet another metric space. I guess technically this integral could go off to infinity, but you could extend the definition easily enough. Okay, so hopefully I've convinced you guys that this definition that we've introduced of what it means to be a metric space is extremely general. There are so many different examples of objects, all of which can be considered metric spaces. And from a computer science perspective, that's a little bit annoying, right? Because we'd like to have algorithms that work with these sorts of objects, but of course, that's a big ask because this is only a weak structure that we've put on our data. And so a very typical thing that we often want to do is to take objects in a generic metric space and then map them into a space that's easier to work with. So the sort of strongest version of this task would be to compute what we can call an isometry. So an isometry is a map from one metric space into another that preserves pairwise distances. So for example, I might think of there being a map phi, right? And then essentially the property is that the distance on one space, like d of xy, is equal to the distance on the other space, like d prime of phi of x comma phi of y. Now, rather than waving my arms around, I probably should write down that condition, but I think you all can probably formulate this easily enough. Again, an isometry is a map from one metric space into another that preserves pairwise distances. Incidentally, I guess oftentimes we think of this map as being bijective. I could imagine defining isometry being bijective or not. It probably depends on what textbook you work from, but it'll be pretty clear in context in this course. Okay, so why are isometries useful? Well, maybe I have some weird, crazy space that is really specific to one application, but if I can map my data isometrically into, say, Euclidean space, there are plenty of algorithms out there that do geometry in Euclidean space that I can then use. And so, in some sense, oftentimes what we're trying to do, for example, when we compute features on our data points, is find isometry or some isometry-like object from some abstract space into a much easier to work with one. Now, before talking about algorithms for how to approximate isometries, the first question we should ask is, when is it possible? So, given an input metric space, when can I compute an isometry of that space into one that's more easy to work with? So, for example, one question you might ask is whether you can always embed a metric space isometrically into Euclidean space. So, remember that Rn, I guess equipped with the L2 norm, is a very specific space, right? That's the space of points that can be described with n real numbers, where the distance metric between those 2 points is the square root of the sum of the squares. That's a very specific metric structure. So you might ask, can I always find an isometry from some other metric space into Rn? Normally, when I'm teaching this class in person, I'd pause and take a survey, but I'm going to ask you to reflect upon this at home. Well, if you think about it, the answer to this is almost certainly not for some finite n, right? Because, for example, the space of all functions on the real line, which is this ginormous space, is a metric space. So embedding that into this finite dimensional space, Rn, really just feels unlikely. And indeed, that's not the case. So, okay, fine, I asked you an easy question, and it has an easy answer. Let's patch up our question a tiny bit. In particular, we can ask a slightly different question. Can we always embed a finite metric space isometrically into Rn? And in fact, I don't even say what n. I mean, it could be that my finite metric space has 5 points in it, and n is like 23, whatever. So first of all, we should make sure you understand what a finite metric space is. It's sort of a very easy object to work with, but I think the definition sometimes can trip people up. A finite metric space is just a matrix, right? So it's just a matrix of pairwise distance values, right? So like a 5-point metric space would be a 5x5 matrix of distance values, each of which is, positive, symmetric, and satisfies triangle inequality. Okay, so we should reflect a bit. It somehow feels like you should be able to do this, right? I'm given a finite metric space, and I want to embed it into Rn equipped with the L2 metric. By the way, I really should add that to the slide here. And, if I have like a 3 or 4-point metric space, and I'm willing to choose any n that I want, it sort of feels like I've got plenty of room to squeeze my metric space in there. Unfortunately, the answer to this question is no. And this is, I think, one of these really surprising and initially counterintuitive results. In fact, let me give you a 4 point metric space that is not embeddable isometrically into any Euclidean space. Doesn't matter what the n is. So here, remember what defines a metric space is a set and a distance function. So I've given you both of these things. And one thing that I'll let you guys check at home is that this distance function d really does satisfy all the axioms of being a metric. But assuming you're willing to trust me on that, let's kind of figure out why this metric space can't be embedded into Euclidean space. So in particular, we have 4 points, A, B, C, and D. And, they have these pairwise distances we prescribed on the slide. Let's start with the second one, which is saying that the distance from A to B is equal to the distance from A to C is equal to the distance from B to C, which is equal to 2. Okay? Well, if you think about it, if I were to be able to embed into Euclidean space, this second property here is saying that A, B, and C form what? An equilateral triangle, right? And even in like 1,000-dimensional space, 3 points can always be rotated so that you're back into a plane, right? So in particular, our picture so far is pretty simple, right? So if I just knew that second fact rather, then I'd have 3 points like that. I think we've all made peace in this course with the fact that your instructor is a terrible artist on the board here. So what do we know? We know that there's A, there's B, and there's C. And the second relationship here is telling us that they are all distance 2 apart from one another. Okay, so far there's nothing too surprising. We're just drawing a triangle, and I'm making it worse by trying to draw on top of it. Okay, so now let's continue in our sort of high school math exercise here and look at the first line. So first line says that there's another point D, which we haven't dealt with yet, and D is distance 1 away from both A and B. Okay, so what do we know? We know that A and B are distance 2 apart, and D is distance 1 from each of these points. There's a unique place, remember, if we're assuming there's a Euclidean embedding, which satisfies those relationships, and that is the midpoint of this line segment, right? So now what do we know? So far, our picture, if we were just given those first 2 relationships, looks something like this. And again, even though I'm drawing it on the plane, like this is R2, even if I'm in Rn for higher n, then just simple linear algebra argument tells me there exists some rotation where I can draw this picture in the plane. So, okay, so what do we know? Well, I've given you a constructive proof so far that the first 2 distance sort of equalities that I've written on the slide here are compatible with an embedding. And in fact, that embedding is unique up to rotation, reflection, translation. But now comes the weird part, and that is this last thing. Now, this last part gives me the distance from C to D. So that, in our picture here, is the length of this vertical line in our triangle. Now, simple high school style trigonometry here, not even trigonometry, just basic geometry, says, okay, well, this is the midpoint of the opposite edge of this equilateral triangle, so this meets at a 90-degree angle. Okay, so if it were Euclidean, in other words, if we were just ignoring the third line on the screen here, what would we know? We would know that D from C, the distance from C to D. I'm realizing, by the way, I'm sorry, this is bad. Your instructor did a shameful thing, which is there's 2 D's, but hopefully you can follow. This D is a point. That D stands for distance. I'm sorry. You can give me a hard time during lecture. Okay, so what should this thing be? Well, we have a right triangle, so this is equal to the square root of 2 squared, which is 4, last I checked, minus 1 squared, which is the square root of 3. Okay, so I'm like double checking. Somebody pointed at an arithmetic mistake in one of our previous lectures, and now I'm nervous. Yeah, this looks right. Okay. Unfortunately, the square root of 3, the last I checked, is not equal to 1.5. So there's a contradiction. Okay, so again, what did we do here? We said, suppose that our 4 points satisfying these distances were embeddable into Euclidean space. Then we end up with a picture like this from the first two relationships, but then computing the distance from C to D, right, just the height of the triangle here, does not give me 1.5. Therefore, even though this matrix satisfies all the axioms of being a distance metric, what it doesn't do is embed into Euclidean space. So asking for an isometry of just a generic geometric space into Rn for any n is probably a little bit optimistic, right? So eventually what we're going to have to do, because we do want to embed our data into n-dimensional space, is we're going to have to approximate, right? The equal sign here is what's so rigid. So let's pause and erase for a minute, and then we'll continue. Okay, so what we've shown so far is that the embedding capacity, which is sometimes a phrase we use, of Euclidean space is not enough to squeeze in every possible metric space. Now, for fun, I thought I would also give you a positive result of a slightly different space that turns out to have a much better embedding structure. Of course, what we give up is all the convenience of working with L2, which comes with a lot of structure that we actually want. In particular, one contrasting example is to work with the space L infinity. Now, the space L infinity is very close to L2 in that in L infinity of Rn essentially is the set of vectors in Rn, but we're going to replace the distance function with a new one, and even in this case the norm, with the infinity norm, which says rather than working with the square root of the sum of the squares, we're going to work with max of absolute value. And one thing that you can check is that L infinity is indeed a metric space. That this object, like when I do the L infinity norm of x minus y, does indeed satisfy the properties you need to be a distance metric. Now, for fun, I thought what I'd show is a small proposition which proves that every finite metric space embeds isometrically into L infinity of Rn for some n. In fact, we're going to basically bound that n inside of our proof by the size of our metric space. It's not going to be a terribly exciting bound. Okay, so notice that this contrasts quite a bit with our previous slide, right? Every finite metric space embeds into L infinity. What did we give up? Well, we no longer can do linear algebra because L infinity doesn't look like L2. For example, it doesn't have a dot product. So is this proposition useful? Maybe not, but it's kind of theoretical interest, and it's a contrasting property from what we had before. So let's actually work out this example pretty much explicitly. So the way we can prove this proposition is just a proof by construction. Okay, so let's move our statement into the corner here, or at least sort of some useful equations. So here's going to be our proof. It's pretty straightforward. So the first thing we got to do is just write down what we're working with. So let's take M comma D to be a finite metric space. So in particular, we can explicitly write out a list of the elements of M, and we'll assume that there's n of them, right? So we know that we can write M is equal to a tuple, well, really, I guess a set of A1 dot 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 AN. Sorry, it's hard to erase on the board, so that's the set symbol for today. Okay, so now what we're going to do is just define our embedding and check that it's correct. So let's define phi, which is going to take in M and map us into Rn like that. But it's going to be equipped with the L infinity norm by the following, where essentially what we're going to do, when we define a map on a finite space, we just have to say what it does to each element of M. So in particular, we'll write that phi of, I'm checking my notes here to make sure we agree, of AK, it's just going to be a tuple of the distance from A1 to AK, all the way, and so the distance from A2 to AK, dot, 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 the distance from AN to AK. So first, let's step back and make sure that we understand what we've just done. So this is a map phi from our finite metric space M into Rn, where the Rn is just a list of n numbers. There's nothing too exciting there. So essentially, what we need to do is for every AK, we need to associate that with some tuple. And now, the only object that we have to work with, in some sense, is this distance metric d. So the embedding that I'm going to define is really simple. It just takes AK, and it maps it to a vector, which is the distance from AK to each of the other AIs. Notice that the kth slot of this embedding is obviously 0. OK, so I claim that this function phi is in isometry. OK, so essentially what we need to prove is that phi, which goes again from M into Rn, is an isometry. So in particular, what we need to do is to prove something about, and this is equipped with the L infinity norm. We need to prove something about that norm. So first, let's write down an expression for what that norm is. So essentially, the distance that we're working with looks something like this. So it's phi of AI minus phi of AJ, L infinity norm. Well, just by definition, this is equal to the max over all indices k of what? Well, it's the max over all indices k of the difference between the kth slot of phi of AI and the kth slot of phi of AJ, which, of course, is the same as just d AK AI minus d AK AJ. Okay, so this is basically gives us the elements of the distance matrix that we're working with and we need to prove something about. Right? In particular, what do we need to show? We need to show that this expression on the right-hand side recovers the original distance metric d between the a's. Okay, so the way we're going to do this is to bound this expression on both sides. That's supposed to be an O. On both sides by d of AI AJ. Okay, so essentially what we're going to do is we want to claim that this is equal to d AI AJ. So we're going to show that it is both less than or equal to d of AI AJ and greater than or equal to. So the first step in our bound is really simple. So what we can do is on the right-hand side of our expression here, we're going to take k is equal to I. Well, what do we know then? This is the max over all k, so the max is greater than or equal to this expression for any fixed I, right? So what does that imply? That implies that phi of AI minus phi of AJ, well, this is a max, so it is greater than or equal to this expression with k equal to I. So what do we get? We have d of AI minus d of AI AJ, like that. Well, what do we know? We know from the diagonal property of distance metrics that d of AI, this is just 0. And distances are non-negative, so the negative here doesn't matter. And what I get is d of AI AJ. Okay, so that showed one direction of our inequality, right? It shows that this L infinity norm is greater than or equal to d of AI AJ. So now we need to show that it is also less than or equal to d of ai aj. So let's do that on the right-hand side. I'm going to sneak my notes to the other side of the screen here. And essentially what we're going to apply is the triangle inequality. Why? Because we kind of expect to have to use all of the structure at our disposal, and we haven't used triangle inequality yet. Okay, so let's do that. Essentially this is just going to apply the triangle inequality twice. Okay, so in particular, what do we know? We know that the distance d from ai to ak, well, remember that triangle inequality tells us that this is upper bounded by cutting through any other aj, right? So this is upper bounded by dai aj plus d of aj ak. And similarly, what do we know? We know that going from aj to ak is always cheaper than cutting through ai. So we know that d aj ak is less than or equal to d of aj ai plus d of ai ak. All right, so these are just two different triangle inequalities, which we know because d is a distance metric. So the next thing that we're going to do is just rearrange these expressions a little bit. Now, in particular, remember that our goal here is to upper bound this quantity, right? So we've got an ik minus a kj. And there's absolute value, so we can also flip the sign. So we've got an ik and a kj. So from the first expression, what do we know? We know that d of ai ak, and now, by symmetry, we can move the k into the first slot. So minus d of ak aj is less than or equal to d of ai aj. Okay, and similarly, well, what do we have? We have a kj here, and we have an ik here, right? So we know the following, right, which is d of ak aj, where did that go? Here, minus d of ai ak is less than or equal to what we're left with, which is d of ai aj. So what do we have? We have d ai ak minus d ak aj is less than or equal to d ai aj. And also minus, right? So notice that these are just flipped from one another. We've got a kj there and an ik here. So if an expression and its negative are both upper bounded by the same value, well, then what did we just show? We showed that the absolute value of d ai ak minus d ak aj is upper bounded by d ai aj. Okay, and remember that this is true for any k, right? So we just said, take an arbitrary k. Sorry, I should have written that explicitly. So this expression is true for all k. Well, what does that mean? That means that, the max over all k is also upper bounded by the right-hand side here, right? So we have, the max over k of this absolute value, maybe we'll just copy it like that, is less than or equal to d of ai aj. But of course, this left-hand side is exactly the L infinity norm that we're worried about, right? So that's exactly phi of ai minus phi of aj L infinity norm. Sorry, this is a little bit messy. I mean, the reality is this is a pretty easy proof, but your instructor is sleepy and has managed to write this in a sloppy fashion. But the basic point here, if I get out of the way, is this inequality here, which is nothing more than the inequality we had in part 1, just flipped backward. So now we know that actually it's an equality, and we're done. So what did this show? This showed that we started with a finite metric space m comma d. We explicitly wrote out its elements, and we took this embedding. This actually has a name. This is called the Frichet embedding. We'll call it out later in lecture. And what we wanted was to show that this is an isometry into L infinity. And we did that by just checking the isometric condition explicitly, right? So we essentially upper and lower bounded this L infinity norm by d aij, which is exactly what we want. OK, so let's erase and keep moving. OK, so hopefully I've convinced you that isometric embedding is a tricky matter. I mean, it depends on the structure of both the source and the target space. Oftentimes it's not possible. And as you can imagine, there are gigantic branches of mathematics dedicated to figuring out which spaces embed exactly or embed well into others. In fact, given the rigidity of this isometric embedding condition, a very typical thing to do is instead to seek an approximate embedding. And there are many different ways to measure that. So for example, here on the slide, I provide you with some sort of standard notions of what it might mean for a function to approximate an isometry, right? So let's say that I have a function f from one metric space into another, and I want to know if it's a good embedding or not of metric structure. So one thing I might do is take mu and rho to be the distance metrics on the two space, and I could measure the three things that I've written on the slide here. So the expansion is looking at the ratio of distances in the target space to distances in the source space and taking the max one, right? So if my map is an isometry, that max, or rather if my map were an isometry, that max would equal 1, right? Because by definition, an isometry is going to have the numerator and the denominator of this fraction be the same. But if f distorts things by moving them farther apart, right, then the numerator will be larger than the denominator, and that max will increase. Similarly, the contraction of a mapping f just flips that ratio upside down and now looks for the max of the distances in the first space to distances in the second, right? So this is measuring kind of how much f shrinks stuff. Notice that it does in kind of a funny way. We think of contraction as a small number, but in this case, the bigger the contraction, the higher my map distorts stuff. Wasn't the best way to phrase that, but I think you follow. And then a typical notion of distortion is just to multiply these two things. Now, this is one of many different measures that people use to tell you whether or not their embedding is good, but it's a pretty useful one. So essentially, the distortion of a map is just the product of the expansion to the contraction, like the pair of points that get stretched out the worst and the pair of points that get smashed together the worst. Now, one thing you might ask is whether there's a good embedding into a different space that doesn't necessarily make distortion equal to 1, right? That would be an isometry, but at least has close to 1. And it turns out that even though we showed that it's impossible to get distortion equal to 1 when we map into Euclidean space with the L2 norm, we can often get a low distortion. So in order to do that, we'll actually borrow an idea from the proof that we just completed of embedding into L infinity. And this is the idea of using a distance metric to make your embedding. So this is sometimes called the Frichet embedding. So more generally, if I have a metric space m comma d, then one thing that I can do is take a series of subsets like S1 to SR here, which are subsets of M. So we can define the Frichet embedding to be a vector of distances to subsets. So for example, in our proof of that L infinity fact, each of our subsets was just, like we had a different subset for each point. In general, by the way, the distance to a set is the minimum distance to any point inside of that set. So like S1 through SR here do not have to be a single point. They could be like different regions in our metric space or something like that. So in general, again, the Frichet embedding of a metric space takes as input some set of subsets of our metric space. And the embedding is a vector of values, which is like the distance to the first subset, the distance to the second subset, and so on. Okay, so we used the Frichet embedding in our previous proof, where each of the subsets were just singleton things consisting of one point. But more generally, you could imagine, like, dividing into 4 pieces or something like that. So there's a well-known result. We do not have the machinery in this course to prove it rigorously, but I've included a link in the slide here to a careful proof. This is due to Borgains, although there are a lot of different variations. There's one by Matusek that improves the bound a little bit, and I think a number of theorems came out at roughly the same time with a similar flavor, which essentially says, given a finite metric space, so a metric space that is consisting of n points, then for every single p greater than or equal to 1, we can embed in an LP, but we incur some distortion, where we've defined distortion using that definition in the previous slide. In particular, what we can do is come up with a randomized algorithm that embeds into LP of Rm with logarithmic distortion, where we choose m very carefully in the size of our point cloud. But thankfully it's logarithmic, so, or at least log squared. So what this means is that if I have n points in my metric space, I can embed into Rm, where m is roughly log squared of n, with relatively little distortion, right? Logarithmic distortion. I think this is a randomized result. I'm actually not sure if there's a deterministic version of this or not, but I encourage you guys to look into it and let me know. So the actual algorithm for Borgains' theorem is quite straightforward. I've put it on the slide here. This is just borrowed from the course notes that I've linked from one of my colleagues at University of Chicago, where essentially you choose m very carefully, and then what you do is you use the Frichet embedding with sets that are sort of whose size goes from 1, 2, 4, 8, 16, 32, and so on. And so what you do is construct these sets by just independently flipping a coin among the different elements of your whole metric space to whether decide to put it into each of the sets S sub I. So there's nothing too exciting here. It's basically like taking really dense sampling of your domain and then sparser and sparser and sparser ones and using the Frichet embedding. And what you're basically arguing is that the Frichet embedding gives you enough information to kind of triangulate on where you are. So this is a nice positive result that's sort of halfway between the two things that we just showed, right? We showed that anything embeds isometrically into L infinity, and in fact is quite easy to construct it. Even 4 points don't embed isometrically into L2. Turns out that counterexample you could probably extend to other LP spaces, but that if you're willing to incur logarithmic distortion, you can embed, and the embedding is pretty easy to construct. It's really not so hard. So in any event, hopefully this discussion just in 45 minutes gives you some idea of the flavor of mathematics that we do in the metric embedding universe. Again, you could easily take an entire mathematics course, an entire algorithms course on computing embeddings of different metric spaces into other different metric spaces. This is a really classical and interesting topic with extremely deep and challenging problems. But our focus in 838 is largely going to be on the practical aspects. So starting in the next lecture segment, we'll talk about some algorithms that really are intended to embed data into some metric space, typically Rn, efficiently and with low distortion. Some of these algorithms will have nice theoretical properties, and some of them will just work practically, but maybe we don't have such a good theoretical understanding because they're based on some non-convex problem. So with that, I'll see you next time.